Yes. I use this to clean the board. That's all I have.
It's fine.
Is it? What happened?
Chocolate.
Thank you, Chew. He's such a messy boy.
No, it's
Such a messy little boy.
it's not my fault.
Messy, messy child. Alright, let's continue, children. Young's modulus. Got that? Chew? Ready? Young's modulus? Yep. Okay. So this Sean. Ready? Young's modulus. Did you write that down?
I said down.
Continuing. Continuing. Okay. So I actually mentioned this word in the last class, but exactly what do I mean? So when we say the deformation of a material, what we mean exactly is the process of changing the shape, or for us, which is the length of the material, by applying a force, which we call a stressing force. So deformation means changing the shape by using a force. That's all. That's all deformation is. So if I deform something, it means I change its shape by applying a force. So if I deform someone's face, it means I change the shape of their face by applying a force to their face. Yeah? The reason I use that example, Andrew, is because you know in English you have these things called collocations. You know collocations? Yes. And deform is one that usually goes with face. So you don't, if somebody's face has changed shape, you don't say, oh, they have a strangely shaped face. You say they have a deformed face. Yeah. You knew this one, Monica, did you? Yeah. Okay, you have that definition? Is that your breakfast, Chew?
Yes.
Healthy breakfast, energy drink and chocolate biscuits. We said he's either in bed or dead. It's one or the other. And if he turns out to be dead, we know who it was. He's already admitted to it. Okay, continue? No. Okay. Continue?
Yeah.
Okay, continuing. Next. The word stress actually has a precise physics meaning. When we talk about the stress on a material, well, actually I wonder if anybody knows this already from any physics they might have done.
Energy.
No, it's not an energy. No, it's not actually an energy term. It's nearly that. It is related to force, but you're not quite right. It's not quite equal to force. The stress on a material is the force per unit area. In other words, it's the force over the area. And importantly, when I say cross-sectional area, what I mean is, if this is my material and I pull it, it's the force divided by this area. This area here. That's called the cross-sectional area. So, what's the unit of stress? Pascal. So it's like a pressure rather than a force. Okay, so this is a new term for people. Mathematically, this formula. Stress is force over area. Be strong, Jerry. Be strong.
I try to be strong.
The heaters are on, aren't they? The heaters are on. I know, no. You need to get used to this. It's only going to get colder. You need to get used to this. This is your life now. Adapt.
But I heard that it's not really like this weather all over the place.
Correct. It's going to get colder.
It's not going to get colder, it's already cold.
I'm sorry, it's going to be like this until March.
It's 2.
Yeah, and it goes minus.
It goes minus.
It goes minus.
No, I hope so.
Why? Why?
Because it is my imagination.
Well, you won't have that problem here.
Yeah, and we want snow.
You won't get snow because we're too near to the ocean. You'll have to move west for snow.
Yeah.
So you'll be cold and no snow, and it'll be dark, and you'll be preparing for a test, and you'll be hungry and cold.
It's so dumb. It's so dumb. I want to go back.
No, be strong. This will toughen you up. Okay. Therefore, the units are clearly pascals, so it's like a pressure term. Now, strain is our second term. Strain has a definition as well. Does anybody know strain?
Jockey. Joint.
Go on, Sean. You might know it actually. I know, it looked like you knew it.
Yeah.
Yeah.
Absolutely.
Just looked like, okay. The strain on the material is the change in the length, which is the extension, over the original length. Basically, the strain is X over L. It's how much you extended divided by the natural length. So a strain of 0.1 means 10% increase in the length. A strain of 0.2 means a 20% increase in the length. Yeah? What's the unit for strain? What's the unit? No unit. No unit for strain. Yeah? Continue? There's no units here. It's unit free.
Duty free.
Not as delicious as duty free. Anyways, we got that? No? Okay, Sean. Yeah? Are we just waiting for Sean? Come on, Sean, you can do it. Ready? Yes? Okay. So now that we have stress and strain, we have this new constant called Young's modulus. I wrote the letter Y, but really I should have used the letter E, but I don't like using the letter E, but that's what they used in the exam in the book, so maybe I should change this to the letter E. I just don't like using E because I'm using that for energy already, but that's what they use in the book, so I think I should change that. Anyways, Y or E, whatever you use. Young's modulus, no, I'll change it. E. I'll change it later. It's the ratio of stress to strain. In other words, it's stress over strain. Let me just... Okay. What's the units for Young's modulus? Well, what was the units for stress?
Newton.
Pascals. And what was the units for strain? No. So what's the units for Young's modulus? Pascals. Pascals. Can we work?
There's no
Yeah. Clearly Pascals. Clearly. Yeah. So, stress was force over area. So is stress constant? No, because you can change the force. Okay, the area you don't change, but you can change the force. Strain is extension over length. Is this a constant? No, because you can change the extension. The length is constant, but you can change the extension. But what Young noticed was that if you take the stress and divide it by the strain, that is a constant, and that is a different value for each material. Now, we'll come back to exactly the use and importance of this in a moment, but we'll need some more terms. Next term is something called tensile strength. Does anybody know what tensile strength is? Go on, Sean.
You can do it.
Yeah. Come on, Sean. We believe in you.
Somebody.
It's a describe a material. Maybe it's a.
Come on, Sean, tell me! I'm dying here!
I will feel. Try again and feel better. I don't know how to.
No, just try, Sean, just try. Don't worry about your English, just try.
Okay. Describe a material. How can it in the lab?
Yes? Yes? Finished or more? Okay, I'm not sure if I understand, but let me tell you what it is, and you tell me if you understand. Tensile strength is the force you need to pull something like a rope or a wire or a spring or whatever to the point where it breaks. In other words, it's the force you need to break something. Yeah? Breaking force, if you will. Yeah? Of course, this is very important in engineering. When you're building a bridge, a building, a home, you need to know the tensile strength of the materials used. You don't want to build something that will break. So tensile strength is how much force you need to break a material. I was watching a show a long time ago. I don't know if you've left Dublin, but when you travel outside Dublin, you'll see a lot of old stone bridges. I don't know if you've ever seen them. You know, small little hump bridges.
Yeah.
Not so big, maybe, 10 meters, maybe less. And they're made out of stone. And nobody really knows what the tensile strength is of these bridges. So you have, ground, river, ground, and you have this stone bridge that's built here. And this stone bridge would be very old. And the problem is, the engineers are now, they're worried. Well, these bridges weren't made for, big trucks to go over them. So they wanted an experiment to see how strong these bridges are. What is the tensile strength of these stone bridges? So they got permission to destroy one of these old bridges. That they were allowed to put these giant poles in the bridge, and these machines, they put a huge force down into the bridge. These big machines, they just push down into the bridge, and they just wanted to keep pushing and pushing and pushing until the bridge breaks, and then they found the tensile strength. And to their surprise, they could not make the machine powerful enough to actually break the bridge. So they don't know what the tensile strength is because they failed to produce a force strong enough to actually break the bridge. So those stone bridges that you see are shockingly strong. The tensile strength is huge. You're much safer on one of those than on a steel bridge, because we know what the steel bridge tensile strength is, and steel bridges do collapse and fail, but not the old Irish stone bridges. They're quite reliable. Okay, so stone has a very high tensile strength. So stone is a better bridge material than steel would be. Yeah. So this is tensile strength, and this is real life. This is engineering. Okay. Let's look at a graph of stress and strain and compare it to force and extension. So let's have a look at what a graph of stress and strain looks like. Okay, so here we'll put stress, and here we'll put strain, and we'll make a graph. Now, Young's modulus is stress over strain. So that would mean stress equals Young's modulus multiplied by strain. This is on the y, and this is on the x. So, what is the slope of this graph? Yeah, Young's modulus. If we draw the graph like this. And if we did the graph the other way, strain and stress, what would the slope be? It would be 1 over E. But anyways, back to this graph. What is the relationship between this and the K that we did in the last lesson? Well, let's have a look. E equals stress, which is that, over strain, which is that. And that's equal to F over X. Now, that's an A. It's like having an A here and an L here. Yeah. But we know what F over X is.
K.
It's K. So E equals K L over A. So in other words, we kind of see a relationship between Young's modulus and the the spring constant K. In fact, the relationship is linear. By saying the K is bigger, we're also saying that the Young's modulus is bigger. And by saying the K is smaller, we're also saying Young's modulus is smaller. The only difference is Young's modulus also depends on the shape. You see, for the spring, we don't care about the shape for the K. But for Young's modulus, we care about the length and the area. So basically the difference is this. Young's modulus is like K, except we need to care about the shape as well. Okay, so that's the relationship here between them. Now on to values for Young's modulus. Oh, thank you. Okay. So let's have a look at different values of Young's modulus for different materials. Of course, you'll need these values for the questions. The first material we'll look at is rubber. Rubber has quite a small K, because you know rubber is very stretchy. Yeah, so it has a small K, and so it has a small Young's modulus. But when I say small is quite a big number here, because it's still 10 to the 9. So this is what I mean by a small Young's modulus. Let's increase the material. Look at something a little stiffer. So after rubber, we'll go on to nylon. Now, it's still small, but it's much larger than rubber. For those of you who don't know what nylon is, Chrissy or Monica will tell you. You know what nylon is?
Nylon.
It's the what?
It's a nylon.
Nylon.
Wow, great. I would never have thought of that. That is true. The nylon bags in the supermarket. That was not what I was thinking of.
Well, I was thinking of clothes.
Yeah, the tights.
The nylon already.
Nylon clothes. It's the stretchy material. Yeah.
In Korean it's nylon also, and in Chinese it's nylon.
It's the same word.
Yeah.
Oh, well then I could have asked Chu to explain what it is then. Okay, Chu, what's nylon?
It's used for the umbrella.
For the umbrella?
Yeah. No.
Oh yeah, I guess it might be. Yeah. And it's used for, you said the shopping bags. Is this back home for you? I think a lot of shopping bags here are plastic. Yeah, like actually a bag like what Andrew has there. Would that be nylon? No, that's kind of like plastic. Yeah. So it's stretchy. It's not as stretchy as rubber though. Your clothes, some clothes have a little bit of, yeah, it would have a little bit of nylon mixed into it. If you look at the tag, it might say the percentage. Are you looking at his raincoat? Step aside, Andrew. He doesn't have a tag. What type of cheap coat is this now? This is some kind of knockoff. It has no tag. Where? Do you have any tag on this?
I don't know. Maybe in the pocket.
No, there's nothing on it.
Oh, I have a tag, but I can't.
It's like 8% nylon.
That's 8% nylon. Okay. So, Chrissy's jacket is 8% nylon. Right, next. Now, we're getting into materials which really don't stretch. Although wood has some ability to stretch. You don't really see it with wood like this. This isn't normal wood. This is a very special type of wood. This is called a high press wood. So this doesn't really stretch if you were to put a force on it. But if you have some, freshly cut wood from a tree, you actually can, you can bend that wood, you can stretch it. If you bought some real wood from a hardware store, it does have a stretchability. This is not actually normal wood. I don't know if you know this, but if you cut this open, what would you see on the inside? Wood. You kind of would, but what? What?
Or is already
Two nose. What?
is
Wood.
this is actually cheap wood.
Very good.
This is high press and
Perfect, yeah. He's right. It's chip wood and it's high press. So they took lots of little pieces of wood and with high pressure bound it together. This is why it doesn't have a stretch. It's also cheap to make. But it means that you have to cover it in a special material. So it makes it look like it's smooth. But if you were to cut this, you would see all the little chips of wood. This is like what they do in IKEA. You know IKEA?
Yes.
Yeah. Okay. Glass. Now does glass stretch?
Yeah.
Yeah, but not much. If you stretch it, it'll very quickly break. Next material is brass.
brass.
You know brass?
Why is that sure?
Yeah, why so shocked?
Brass. Okay.
Yeah, but you seem so shocked, like I said a bad word or something.
What?
I just nothing.
Brass with a B. Just to be clear. Yeah, brass.
The metal. The mixed metal.
Yeah.
Oh.
What is brass made of?
Full.
Isn't it copper and bronze or something? Nickel? Copper and iron? Huh? Yeah. Anyway, it's a mixture of two metals.
Copper and zinc.
Copper and
Zinc.
zinc.
Yeah.
Oh.
Really? Okay. Brass. Next is copper.
Yellow copper.
And then after copper is steel.
Brass is is big
That's what Chrissy just said.
Listen to me.
Right. Next is steel. Steel, as you can see now, these are all 10 to the 9. You can see this is compared to this is quite different as we move up. Next after steel,
Diamond.
no. Graphene. That is what is made in your pencil. You know the. I know. It's mad, isn't it? No, this isn't tensile strength now because we don't know what force is required to break it. This is just Young's modulus, which is, as we said, it's kind of like a K term. It's a measurement of stretchiness. So what I'm saying here is graphene, what's in your pencil, is not a stretchy material. You can't really stretch it easily, like steel.
So this is like a stretching, huh?
It's like a stretchiness.
Okay.
It's like a K. Now, Monica, it is possible. You know, it is actually interesting, but there might be, I don't think there really is a relationship between Young's modulus and the tensile strength. So just because the material is not stretchy doesn't mean that it has a high tensile strength. For example, both these materials are quite difficult to stretch. But I feel that the tensile strength here is actually bigger than here. Because I feel like graphene is easily broken. You know, another example, you might have it back home, is porcelain. Do you know porcelain?
Yeah.
Does everybody know porcelain? Porcelain is what they make the cups from. You know, the expensive teacups. The material used to make the teacup is porcelain.
Oh, I don't know. I know that in Latin.
Okay. Does everybody have teacups back home? Like nice teacups that your parents don't use every day? Fancy, expensive teacups. No?
Made out of glass.
No, made out like a clay, like a white material.
What?
Yeah, the material is white, and sometimes the cup is painted.
Yeah,
Yeah,
Chinese teacup.
like Chinese teacup.
Oh,
Yeah, I have it.
You know this material?
This is clear, right?
It's a type of clay. Now this material is called porcelain. This material is interesting because it has a very high tensile strength. So you can actually, if you are very careful, no, not this. If you're very careful, you can stand on it without breaking it. Stand on the cup without breaking it, if you're careful. So it has an ability to take a high force before it breaks. But what it does not have is a high Young's modulus. In fact, it has a low Young's modulus. And not only that, I said that backwards. It has a high Young's modulus, but it has a low elastic limit. So if you try to pull it, it'll be quite hard, and very quickly it will reach its elastic limit, which means it cracks and will not return back to its original shape. But yet it has a high tensile strength, meaning if you're careful, you can put a lot of force on it. Basically, it can take a lot of force, but not quickly. So if you throw it, you will break it, because the force applied is quick. But if you stand on it slowly, it has an ability to take a high force. Anyways, don't need to worry about that. These are the values which you need for Young's modulus. Okay. Let's have a look at an example. A boy hangs a 100-gram mass at the end of a 1.5 copper wire, which is attached to the ceiling. The wire is 2 millimeters thick. Okay, let's draw that. We have a wire, hangs from the ceiling. It is 2 millimeters thick, and it's 1.5 meters long, and there is a 0.1 kg mass here hanging from it, and it's made of copper. So what's the Young's modulus for copper, did I say? Okay. Part A. What is the area? The cross-sectional area. This area here. So what formula do we need for the area here? No, they were right. Pi r squared. What's the r here? 1 millimeter. So that's 10 to the minus 6 pi, which is 3.1415 times 10 to the minus 6 meters squared. B. Are you okay with that so far? Yeah. B. What is the stress? Okay, what's the formula for stress? Force over area. What is the force in this example?
0.1.
Yeah, the weight. And what's the weight? mg. And what's the m? 0.1 g. So what's that? 0.981 over 3.1415 times 10 to the minus 6. So what's the stress here, please? What does it say again, Monica?
312.38. What? No.
That seems reasonable, doesn't it?
312.271. 0.208.
3.12. A 1, a 2, a 3, a 4, a 5. Times 10 to the 5 pascals. C. What is the strain? Okay, what's the formula for strain? X over L. Now, do we know the X? No. But actually, what you can do here is, we could actually use the formula Young's modulus is stress over strain instead. Because what we can say is, the strain equals the stress which we know over Young's modulus which we know. So 3.12 times 10 to the 5 over 117 times 10 to the 9. And what do we get, please? We should get a small number here. Okay. D. What do you think I might ask you next?
The K.
No.
The X.
Yes. By how much has the wire extended? What's the X? So we know that strain, which we've worked out, is X over L. So that means X equals L multiplied strain, which equals 1.5 multiply 2.67 multiply 10 to the minus 6. What do we get?
4 times 10 to the power negative 6.
So that's equal to 4 micrometers. Okay, so far? And finally, what is the K? So we know in the picture there's two forces, an F and a weight. So we know that Kx equals mg. So that means K equals m, which we know, don't we? Yeah, we do. And the g, which we know, and the x, which we've just worked out. So that is, what was my m? I forget. 0.1. Yeah, so that's 0.981 over 4 times 10 to the minus 6. So that would be a pretty small number for copper. Sorry, big number. What do we get? 245,250 newtons per meter. Yeah, it is. Now that formula is not in the formula book and you're not expected to know or use it. So we can use it if you know it. Yeah. Okay. Continue? Yes? Right. Next one. This one isn't really that good. It's kind of stupid. Yeah. Now, I like this first example because this is a good example of all the different things they can ask you to do. In the exam, I find that Young's modulus is usually a nice question. And it's... I can't... It was difficult for me to kind of think of difficult questions. But I did my best anyway. So can you try these questions for 5 minutes, please? And then we'll finish. So it's on the next page. You'll need to use the table of values you got.